My first lecture would be just an introduction to the quantum mechanics and how and why have it emerged. So I will begin from the very beginning, the classical physics. In classical physics, there is a couple of basic assumptions in classical physics. Every object in classical physics is described by so-called dynamical variables. These variables can be either coordinates, not either, both coordinates and momentum of the particle. So if you have the particle, if you have some particle, uh, uh, point-like particle, how could you describe this particle in classical physics? You you say that it has some coordinates in some coordinate system, and it has some velocity vector, or you can say it's projections of the velocity on some axis. So this, or in other words, you can, you can speak not in the terms of velocity, but in terms of momentum, which physics prefer more, and you can describe the particle in terms of let's say in 3D world, you describe particle with 6 values, 3 coordinates and 3 momentum projections. So and that is the so-called dynamical variables. What do we mean saying that is dynamical variables? We mean that for every particle we can assign, at every moment we can assign these 6 values, and we can accordingly we can just say that we can describe the movement of the particle by attributing the dependence of the coordinate on the time, or the momentum on the time. You know that the momentum is just in this simple case. In the simple case, momentum is just a derivative of the coordinate. If we say that that's a vector, r is mass time r. So you can describe by this this time dependence every movement of the particle. The next important thing of the classical mechanics is that its evolution equations. They are so-called first-order differential equations. Because so you can, what does mathematically? It means that you can say that first derivative of the momentum equals to the force, which depends on the 3 coordinate. So, but what does it mean physically? Physically, it means that if at some point of time, at some moment, you know the coordinate of the particle, all coordinates of the particles, and all momentum projections or velocities, which is quite the same. You can predict every movement of this particle in the future in billion years. So in arbitrary precision. That is the classical physics concept. So classical physics concepts presumes determinism. You can determine any future. You can predict any future events. Any events in the future, if you know all information about the system at the beginning. In the real world, even if we do not think about the quantum mechanics, real world is um, bit complex, because real world consists not one or few particles. It consists of 10 to, let's say, it consists of 10 to, let's say, 25, 10 to 30 particles. And you can write down the equation of motions for these particles and solve this equation. So that's how molecular dynamics works. But you cannot give precise, you can obtain precise boundary initial conditions for this system. And all this equation would be so not only so hard to solve, but they would be very, very sensitive for the initial conditions, and they would be very, very hard to solve. So no computer, no real system can be described by this approach, unless you have not this amount of particles, but if you have 1 million particle, there is a computer simulations, microdynamics, that can describe the behavior of the system of the million particles. But still, it is not so precise as you want. If somebody of you have acquainted with the molecular dynamics simulations, they are not so good in describing the real world. They're good, but they cannot do it precisely, and you need to contribute a way more force to do it well. So everything worked perfectly before the end of the 19th century. You can, as a physicist, you could describe, you can write down equations for any known type of objects, and even if new information emerged, you can put it in this major doctrine, which assumes determinism. So major doctrine combines the determinism that we can unambiguously determine the future of the particle if we know its presence. Sorry. And yeah, and this picture worked well, because when the people understand that there is something else apart from particles, I speak about the radiation, about the electromagnetic field. They wrote down the Maxwell equation that describes the evolution of the electromagnetic waves, and they would say they kept this dogma, but they introduced new dynamical variables for which for electromagnetic waves are the distribution of the electric and magnetic fields in the electromagnetic fields in the space, and distribution of the charges. I would say R and T. So if you know the initial distribution of the charges and the electromagnetic fields, you can precisely describe how the electromagnetic fields and the charge will behave at any moment in the future, including the billion years. By the end of the 20th century, another concept, another important experiments showed that our information about our knowledge about the space and time is not full, and we need to adjust this information. I'm speaking about special relativity theory and um, general relativity theory, and in the same time, these both general relativity theory and special relativity theory did not uh, didn't pushed out the main dogma of the classical physics, the determinism. The particles still could be described by by the first order differential equations, but the Newton's equation didn't work. Einstein showed that the Newton equation should be adjusted somehow to describe the behavior of the particles in the that moves at very large velocities, or that are in the very strong gravity fields. But the whole basic of classical physics still still kept, because you can either in field theory, electrodynamics, or special relativity in relativity theory, you can describe every particle or every point of the space by the dynamic variable, would it be or electromagnetic field, or just a velocity, momentum, and coordinate of the particle. And you can write down the first order equations which describe the evolution of the theory. So during the entire period before the beginning of the 20th century, every single experiment and single physics discovery didn't question the validity of this concept. But what we're gathered today about is that there was some experiments that stuck physics, because they physicists, because they could not explain it in the concept of the classical physics. Yeah, I must say that by the end of the classical era, the physicists knew that the whole world, everything that we can, I'm sorry, everything we know about the world, we can describe either as a particles, or radiation or field, radiation, or field. So that happy development continued until about the beginning of the 20th century, until some experiments emerged that show that we cannot explain the world in this simple this simple division of the particles and radiation, and describe them using the deterministic concepts. Sorry. So, what about the radiation? Sorry, can I, just for a couple of minutes, listen for a minute, can I go out? I'm sorry. I'm sorry. So what about the radiation? There was a there was a huge problem about so-called black body radiation. Um, uh, the black body is some object, some imaginary object that emits light, emits radiation according its temperature, and you can calculate the intensity of the radiation as a function of the frequency of this radiation. That's this equation which governs. I'm sorry. That's equation that's governs the dependence of that's the intensity of the radiation. That's the frequency of the radiation. That's the temperature multiplied by Boltzmann constant. That's speed, light velocity, light speed. So let's do it that way. If you look at this equation, looks good. But if you draw it, let's draw it. It's just a parabolic equation, a parabolic function. We can draw it. Sorry. Yeah. Yeah, it's some parabola. It's a bit bad parabola. Let's make it more. Let's do. Yeah, that's the parabolic intensity. Frequency. And you see that higher the frequency of the radiation, the more is the intensity, and the total energy of the radiation can be calculated as the integral of the of this intensity over all frequencies. And you see that as it is the quadratic intensity quadratically depend on the frequency, the overall integral will diverge. You cannot integrate. The overall energy would be infinite. And that was the problem, because in real life, black bodies, they do not emit infinite amount of the energy. And for this, Max Planck, he hypothesized that the exchange of the energy between matter and radiation, so the matter can radiate the energy not continuously, but transferring in a discrete portion of energy. And this portion of energy, they depend on the frequency in a such. I can take maybe the red. Yeah. That is the famous equation. That's the famous equation. The energy is linearly depends on the frequency, but you cannot transfer the energy less than this portion if you have only if you have radiation only with this frequency. So, and this assumption led to the following equation for the light intensity. And if we describe it, how we do it, okay, let's do it in that way. Yeah, if we draw this. If we draw this function, we will see that it coincides with this equation for some time, but at high frequencies it drops, and it has some maximum. And this new dependence, it worked well, and it could predict the experimental results, experimental data, and moreover, it could solve this problem of the black body radiation. And you understand that um, if you decompose, if you approximate this equation at low frequencies, this equation will become the classical one. So that was the one problem, but you must understand that when Planck hypothesis appeared, it seems unacceptable because there were no reasons to describe the radiation by portions, and majority of the physicists they saw it as a convenient mathematical trick, but not a real physical explanation of the black body radiation. So the another problem, experimental problem, was the so-called photoelectric effect. You know that um, uh, if you have some metal plates, you can emit photons from this plate by radiating it by the photons, by the light. I'm sorry, by the light you can emit the electrons. And what is interesting in photoelectric effect that during the photoelectric effect, it depends on the not so much on the intensity of the light, but on the frequency of the light. If the light frequency is low, let's say that's some minimal frequency. If the light frequency is low, you cannot emit electrons from the metal plate, no matter intensity of the light is. So even you increase light intensity very high, if you increase it for high values, you cannot emit the electrons. But if you pass this critical frequency, you can emit electrons even at very low intensities. You will obtain a very low amount of electrons, so it would be a very small current, but you can find them. But at lower frequencies, you cannot find any electrons. So the classical theory cannot explain this phenomenon, could not explain this phenomenon. Actually, there is some very complex paths that can explain this fact, but I wouldn't speak about this today. But usually describe that photoelectric effect also questions the radiational nature of the light. And the last experiment I want to not the last the last experiment I want to talk about in the term in the matter of radiation is so-called Compton effect. Compton effect, if you had your electrodynamic course, you know that if you have some free particle, let's say electron, and if you emit light, if the light bounces the electron, the light is scattered at all directions. This direction, this. That's so-called Thomson scattering. some scattering. Thomson scattering. But during the Thomson scattering, the light scatters at all directions, but it do not change its frequency. It cannot change its frequency. But Compton discovered in 1922, he discovered that if you scatter the light by the electrons, this light actually changes its frequency, and this one contradicts classical view of the classical electrodynamics too. So that's a few experiments from the whole lot that show that at the beginning of the 20th century you have plenty of observation that undermines the classical concepts of the radiation. The next thing, you can assume, you can solve this problem. You can try to solve this problem, saying that okay, I admit that the light is not the wave. The light is just particles moving in the space, and I can call these particles photons. And it can solve these experimental problems. But if you admit this, that the light is a particle, you will obtain the another problem. The so-called, this problem is called interference or diffraction. And this problem emerges in so-called double-slit experiment. If you emit light from if you put the light through the two slits, you will obtain, if you know optics, the interference picture. If this light would be if this light are the particles, imagine what would it be if there is light source. If there is only one, if there is only one slit, the lights go here. I'm sorry, it's not a very straight line. And here you can find only one peak, so that would be the light region. It will go somewhere here, If you have the slit here, if you have the slit here, light goes here, and you have the light spot here at this point. So if you're pushing classical particles through the double slits, what you would find? You find just two bright spots. Imagine that you have two slits, and you and there's a sand that goes through the slits. You will find only two. Two hills of this sand, not the interference picture. But in the actual experiments, you find the interference picture. Okay, you can say that this interference picture comes from the interaction of the particles between the particles. So photons interact with photons, and their combination gives this strange interference picture. But if you will put the light, if you decrease the intensity of the light to the limit of the just one light particle through the slit, you will find what you will find. The first particle will go here, then it will go here, maybe here, 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 and when you put a million, billion particles, billion photons through the slit, you will obtain the very same picture. And so that's the question: what these particles interfere with? If they go through, if they go through the slits by themselves, by alone particles, what and that is the question the classical physics cannot answer. And if you assume the classical physics picture, you cannot answer this classical physics picture of the radiation. You cannot answer this picture, this phenomenon. So the next, please, guys, let me know if everybody knows about that, and I can skip this introduction. So I will assume that everybody interested. So atoms. The another problem was with classical physics was the description of the behavior of the atoms. By the end of the 19th century, people understood that the atoms can emit or absorb energy by only by some portions. They could be described by some very narrow spectral lines. So they could uh, they can irradiate the energy or the light only at the mm, uh, narrow regions of the frequency. Uh, it could be seen in that kind of a picture. That's the spectral lines of the hydrogen, helium, neon, sodium, mercury. So and that is the frequency that can be emitted by this atom. And hydrogen can emit only the light with this frequency, this, and all this. And that's um, unique footprint of every atom. Actually, it's how the astrophysicists work. They measure the spectrum of the light coming from the distant planets or stars. I would say more stars than planets, and then they can describe what atoms, what even probably molecules can be found in these stars. And then, if you are familiar with Hubble, they can and the Doppler effect. They can even measure the distance to this objects from this law. And if you combine these atoms, you can if you have some mixture of this atom, you can have these spectroscopy images, and then decompose these images into the single atom and say what atoms do you have. So this means that not the large objects, but very, very small objects can emit and can absorb or emit energy at some portions. And this portion was not so fixed like in photons, but it was unique for every atom. And in 1930, Niels Bohr he proposed the general scheme explaining atomic spectra, but it was a pure I forgot the word. It was not a theory. He just combined this known. This was a phenomenological theory. He didn't understand the basic why does it how it becomes, but he explained. He built some model which explained this. Which not explain but describe that um, the atom spectra, and he postulated that atoms, the electrons in the atoms can exist only at a certain number of stationary states, by characterized by certain energy. So when you uh, so when the let's say that's the energy, and electrons here can be here, 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 and electrons can go, um, we can take the green line, yeah. Electrons can go in that way, or that way, or they can go here or here, and all combination of this possible transitions by going they emit photons, and all combination of these possible transitions, they describe this they brings us to this possible to this line spectra. That's the energies, that's the energies of the transition from first or second, or so. That was Niels Bohr assumption. Actually, it was, if you're familiar with dynamics, there was another problem. You know, the hydrogen atom. What is the hydrogen atom? The hydrogen atom is the just positive. It's a proton and an electron that orbits around the proton. And if you're familiar with the electrodynamic course, you know that the particle that goes around, it tends to emit the light. It is so-called dipole radiation. If the particle has some um, if the particle's velocity changes, it should emit some light, and that's and by changing, I mean, if the particle has acceleration, it should emit the light. And if if you circle around some point, your velocity every time is changing, it changes its direction, and you have uh, this acceleration that is directed from the center of the circle to the particle. That's acceleration. And if you calculate accurately, you will find that in this picture, the electron should drop to the center, to the proton, to the center of this potential. I'm not sure about the figures. It is either minus, it should be 10 in minus 12 seconds. So the hydrogen atom shouldn't live long. It should live about 10 minus 12 seconds. And then the electron should just fall to the proton. That is according to the classical electrodynamics, but it does not happen. And I think that's the last experiment I want to speak about is Otto Stern and Walter Gerlach experiment. They measured the projection of the magnetic moment of the silver atoms and found that the projection of the atoms, they projection of the angular moment is not a continuous value. That's the memorial table at the university where they conducted these experiments. So they put the beam of the silver atoms through the magnetic field, and these atoms, they decline the straight way depending on the projection of their angular momentum, the magnetic momentum on the z-axis. And if you have if they had the classical particles, they would expect this simple one peak, because there is some average or maximal amount of the maximum amount of the particle with some projection of the angular momentum on the z-axis. It should be, I think, 0, just for the symmetry. And there is some another amount of the particle with another projection. But what they found, that the particles can have only one or other. That's the real picture of this experiment, the real photo they found in the experiment. So what they found, that the particles can have either one, I would say, we can say either up or down value of the angular momentum. So that was incompatible with the classical theory too. Yeah, we almost at the end of the introduction. So why does this picture? Okay, let's think about this Bohr concept of the atom. Let's assume that some particle can be at the energy level E1 and energy level E0, E0, and cannot obtain the energy somewhere in between. In classical mechanics, you cannot, probably you can, I'm not sure, but I do not know any examples how you can build, you can build the system that can that have only discrete energies. Moreover, you can show that it is impossible in the classical physics that the particles can drop from the energy level E1 to energy level E0, because in classical physics the particle, as I said in the beginning, particle's future is totally described by its presence. And if the particles at some time at the level with energy E1, then you can somehow describe, in classical physics, you can describe the evolution of the particle, and this evolution, the energy with time, it should be somehow this one, this E0, this E1. But in real world, you find that in real world the energy drops in that way. It's E1, then it drops, and it's E0. But we have said that, sorry, it's E1. We have said that knowing initial conditions, you can definitely describe the future, the evolution of this. And if you know that evolution, and at this point of time, you can predict that the particle energy drops at time t, moment t. But let's consider this moment. So that's the value delta t. So you can predict that the particle falls at value delta at the moment delta t. But let's consider this moment. This moment do not uh, do not differ do not differ doesn't differ from this moment at all. It's the same states. So using this prediction, I would say that still particle should fall at some time delta t. Okay, let's go here. Point, and also it's delta t. So in this picture, the particle should never fall, but in real life it falls, and actually we know from quantum mechanics that it falls randomly at random time. You can predict only distribution of these times. So that is very large contradiction with classical view of the physics. So, by the beginning of the 20th century, there are two classes problem has matured in physics. Uh, uh, this this problem was, the first one is that the light could not be described as a wave. It should be described of the at some experiments. It should be described as a particle, and in some experiments it should be described as a wave. But nature do not work it in that sense. You should be able to describe the photons, the light, and by the one concept. You cannot choose one concept for this experiment, one concept for this one. And the another problem was the discrete spectrum of the atoms. The classical physics is not capable to describe this concept. So at the next part, I will speak briefly about how people have solved this problem. So, what was the solution of this problem? Of these problems, there was two solutions. The first one was found by Werner Heisenberg, and it was called matrix mechanics. He critically analyzed the experiments on the quantum mechanics, not experiments. He critically analyzed the whole view of the world at the microscopic scales, and he said it's not only his idea, but he applied this idea that in any physical theory, one should distinguish concept and quantities that is are only physical observable, and only these quantities concept should be accounted in physical theory, and unobservable that quantities that you cannot measure in principle, they should be omitted. And using this principle, he built so-called matrix mechanics, in which he described, if we speak about the atoms, he described the system. If we're speaking about the atoms, the electron at the atom, in the terms of the energies. What do I mean by the and the discrete energies? What do I mean by the by observables? Assume that you have electron at the orbit. So that's the proton, that's the electron, that's a hydrogen atom. That's not a perfect circle, but in real world it's perfect. Let's ask yourself, can you measure in principle the trajectory of the electron around the proton? And okay, how can we do that? How we measure the trajectory for any classical particle. We emit the light. We measure it by our eyes or by photographing it. How it happens? The light comes from the sun, uh, from the lamp or laser, hits the particle and scatters to the camera or our eye. And it works well until we consider microscopic systems. If we consider the atom and the electron, the mass of the electron is 10 to minus 30 kilograms, or as they say, 9 times 10 minus 31 kilograms, which is quite the same. And if you so you need to measure the position of this electron. You need the light, the photons that do not should not disturb this electron. So these photons should have very small energy. What does it mean? That means that they have small frequency, and that means they have large wavelength. Wavelength is just speed of light divided by the frequency. I'm sorry for my drawings. So the but what does the large wavelength mean? From the optics and all this thing, what is do you know what is the wavelength of the optical? What is the optical wavelength? I'd say red light. What is the wavelength of the red light? Does somebody know? Not precisely, but just order of magnitude. Okay, the light frequency is about hundreds. Red light probably it's about 600. I can be mistaken. 6, 7, or 5. It's a 600 of nanometers. So it's 6 times minus 7 meters. Nanometer. Yeah, it should be 6 times 7. And what is the size of the atom? And the size of the atom, that's here I can mistake a lot, but it should be about 10 to minus 12 meters. Give me a second. Give me a second. No, I was mistaken. It's about
minus 10, I think.
Yeah, you're right. Thank you.
You're right.
It's more about minus 10 meters. And you see that the size of an atom, the size of this orbit, is about 3 or 4 orders of magnitude smaller than the wavelength. And that means you cannot measure the position of the electron with the optical frequencies, because you can, by the light, you can measure the position of the objects up to the wavelength of the up to the wavelength It's sometimes about two wavelengths or half length, but the order of magnitude is the wavelength. So you cannot measure the values that is sizes that is much less than this. But okay, you say no problem. Let's take the light with a wavelength about 10 minus 11 meters. But we know already that the difference of the energy, the energy of spectrum of the atom, the hydrogen atom, is lies in the optical diapason. So the energy of this light would be about 10 in 4 or more times larger than the energy of the um, energetic orbits energy spectrum of the atom. And the light of this with this frequency, actually it's a gamma radiation, will break this atom apart, even light with that small. So what does it mean? It means that if you try to measure uh, mm, by Gentile soft radiation, you will have a very large uncertainty in the position of the electron, which is much larger than the size of the atom. And if you will measure it by, if you want to have a certain information about the position of the electron, you will have very large uncertainty in the momentum of the, or the velocity of this electron, because it will just go away, it will break apart this atom. And that means you cannot measure the trajectory, because knowing the trajectory means you should know both coordinate and the momentum of the particle. So that's the very basic thing. You should understand that's not, we cannot measure the trajectory of the microscopic particle, not because we have no the precise instruments yet. It's the fundamental problem. There could not be any instrument, and um, we can prove it, that there could not be any instrument that can measure this trajectory. So what Heisenberg says, that we should omit this concept of the trajectory. We should forget about that and work only with this with concept of the energy levels. Further, we will see that there is much more. Uh, there are another ways of working with, not only with energy levels, but in other we can use in other values too. But at this time, and at his matrix mechanics, Heisenberg matrix mechanics, all equation was the matrix equations, and all values was described by matrices. And you know that matrix multiplications are not commutable. You know that if you A, B, and are matrices, that not necessarily AB equals to B times A. And this the fact that matrices are not commutable, uh, uh, they bring us to a whole new world of physics. The another we will speak about this a bit later in the course, just introduction. The another way of thinking was the Schrodinger's approach, the Schrodinger so-called wave mechanics. He applied the ideas of Louis de Broglie that that assume that not only light can be a wave, but any particle can be a wave, can be described as a wave, not a point-like particle. And so Schrodinger described every particle as a wave. and he wrote down his famous Schrödinger equation, which described the evolution of these waves, the evolution of the waves of the particles, and both conception metrics and wave mechanics, they help to solve this problem, and they were able to describe all these experiments, strange experiments that was found by the beginning of the 20th century. A bit later, two years later, Schrödinger showed that wave mechanics and matrix mechanics are equivalent, and so from now people know that it's equivalent picture, but at some for some problems it's more convenient to use Schrödinger approach, and some problems it's more convenient to use Heisenberg approach. But people know that it is the same. They both describe the same theory, the quantum theory, and you know the rules, you know the mathematical rules, how to transit from the Schrödinger picture to Heisenberg picture, and vice versa. So, waves of the matter. We're first what we will speak about is the wave mechanics, the Schrödinger wave mechanics. The main idea was, you remember that the Planck said that the energy of the portion of the light can be emitted or absorbed by the portion, and these portions are linearly depends on the light frequency. And the idea of the de Broglie was that not only the light but any particle can be described as a wave, and the energy of this particle is equals and the frequency of this particle, the frequency of this wave is nu, and the energy of the particle is described by this equation, or alternatively, it's the same equation, h omega, where omega is so-called cyclic frequency. Omega equals 2 pi times ordinary frequency, and h bar, which Planck constant, equals to h divided by 2 pi, where sorry, not okay, where h is 6.6, I forgot about, maybe 4 times 10 minus 34 joule per times second. No, it's h, not h bar, but h. I'm sorry, it's just h. So h bar is something about 0.34. I'm sorry if I've mistaken these figures. It's joules per second. So, okay, the particles are the waves, but we know that the particles are not the plane waves. They are localized at some region, and so we should the first wave we know about is the plane wave. It can be described by this equation. So the amplitude of the wave is proportional. It's an amplitude, the maximal amplitude, and that's oscillating exponential. It's just a plane wave, which is what does it mean? What plane? It means that it changes only at one direction, which is described by this vector k. Vector k describes the direction of the movement of the of this wave. And let's say that is z direction, and in the plane of y, in xy plane, the the amplitude of the wave is equal. So it's like the wave changing only on one direction. It's like just a plane transferring from one point to another, moving plane. So that's the plane wave, but the particles cannot be described by plane waves because we know that particles localized, the plane waves are not localized. And what we need to plane wave. What is a plane wave? If we z direction, just some kind of oscillating function that is not localized. But what we need is some kind of localized, some kind of localized, localized picture, kind of that. That's an amplitude. We need something like that. That's not time. It's not time, but coordinate. So we have non-zero amplitude, non-zero. We can find the particle around some x naught, and can find it far from this point. That's the concept of particle. So let's look more precisely on this plane wave. Somebody of you knows, majority of you knows about that. Somebody probably do not know. This equation describes the plane wave, which has the wavelength lambda shown here. That's the wavelength. It's 2 pi divided by absolute value of k. K is it is called the wave vector, and this you can see that if we write down this this equation in 1D and one dimensional, it reads as follows: kx minus omega t minus omega t, and the value in this parenthesis is called phase, the phase of the wave, phi. And you see that the phase is constant. Phase is constant when this this expression, the bracket, can be described by this equation. And if we rewrite it, we can find that x equals phi. Sorry, let's do that way. Let's write kx equals to phi plus omega t, and x equals to phi time divided by k plus plus omega divided by kt. What you see here, and what you see here is just an equation of motion. That's the coordinate. That's in classical physics we'll call it initial coordinate, and in this value in classical physics we will call velocity. So the phase propagates with velocity omega divided by k, and that is why this value omega divided by in 3-dimensional we should divide by the absolute value of k. It's called the phase speed, phase velocity. It's not a speed, but velocity, phase velocity. I should apologize for my my scripts, because it's just a very first draft. It's Google Translate from my Russian script, so it's a plenty of mistakes there, translational mistakes. So that's the phase velocity. now we know that, so if we know uh, frequency of the wave and the wave vector, actually the frequency of the wave can depend on the wave vector, and phase velocity can be found as frequency divided by k, the absolute value of k. So let's now we know everything about the plane waves, almost everything. Let's move to the actual particles, which should be described by by some the kind of shape. How can we do that? The easiest way is decompose this dependence. Decompose it on the plane waves. Someone of you, or majority of you, knows that. Here's the decomposition. What he has written. What is written? Integral, or equivalently the sum of the plane waves with the values k, with the wave numbers k and frequencies omega. Please keep in mind that omega depends on k. And the amplitude of each plane waves is defined by function f of k. So that's just a sum of plane waves with amplitude f of k. Some of you, or majority of you, knows that it's just a Fourier decomposition, which is that's a Fourier image. That's the in real time and real coordinate. So then we need to describe what is the physical meaning of this wave. In electromagnetic theory, if we describe the magnetic or electric field, E as E naught times, well, let's say E time Ek kx minus omega t, or we can describe it equivalently as sine wave, sine kx minus omega t plus some initial phase phi naught. This amplitude can be measured directly, because we know that the force that acts to the charged particles is the charge times electric strength. Alternatively, we can measure it. You know that the light is an electromagnetic field, and the intensity of the light is proportional to the square of the energy. Not energy. I'm sorry, of the electromagnetic field amplitude. And what is the intensity? What is the intensity of the light? The intensity of the light in the ordinary experiment is just the how much photons have fallen to the some point of. If you have here a lot of photons, that's not so much photons, you will say that the light here is not so intense. It's intense. There is zero intensity. It's more intensity, lower intensity. So the intensity is number of photons, number of light particles that are that is absorbed by the photometrics or some photoplast film. And in the terms of single particle, we can say that the intensity is the probability of the photon to emit of the to drop to the particular point of the film of the or matrix of our camera. The same way, we can say that this function psi it describes the amplitude of the particle, naming that square of the absolute value of the this wave function gives us probability to find the dr probability to find the particle at some point r around dr within the some region of the width dr. Why this this comes where this dr comes from? It's you see that the probability of finding the light here, if we take the large region, the probability would be large, and we take small region, if it is very intense, the probability would be smaller. So we have to speak about not the probability but the density of the probability. So squared amplitude of the wave function is the density of probability, and the function itself is called the amplitude of the probability, just as we call the electromagnetic wave amplitude, the amplitude of this E, just as we call the electromagnetic field an amplitude of the wave, and we call the square of the this amplitude by intensity. So if there's no question, let's move further. If we are speaking about the one particle, the probability of finding of this particle at any region of the space should be 1, because we should find this particle at some point of the space. That means that the integral of this probability over the whole space, that's the integral of whole space, should be 1. And this equation is named condition of normalization wave function. Of course, the wave function shouldn't oblige to this condition, but it is much more convenient for us to work with this with function that obliges this condition, because if the function oblige integral equals to some a, then the probability of the particle would be not psi rt times square dr, but we should divide it by this value a. That would be probability if our function is not normalized. If our function is normalized, a equals to 1, and we shouldn't divide it by a. So note another thing, that in this equation you can describe the wave packet. We call this thing as a wave packet because it's the sum of the plane waves. It's a kind of a packet of the waves, and this wave packet can be described equivalently by the function psi, a function of a coordinate and the time, and equivalently can be described by function f with distribution of the amplitudes of the plane waves on these plane waves are wave vectors, and additionally we should and the additional information is the this dispersion law, this dependence of the um, wave frequency on the wave vector. This dependence is called dispersion law. Dispersion law. We will discuss it a bit later. So if we have this, let's speak about this wave packet, which should describe our particle, because only the wave packet of such shape describe localized particles. Localized means that we have almost zero probability to find particle far away from some point, and we have non-zero probability to find particle around some point. So it's a psi RT. Let's say it's x value. So let's consider some wave packet which is localized at the region delta k. So that's some k naught. That's the k naught minus delta k. Sorry. How we would do that? Oh, we would do that in that way. Yeah, that's the point k naught. That's the point k naught minus delta k, and that's the point k naught plus delta k. So the particle localized at the sum region, not the particle. I'm sorry, that's my mistake. It's not k naught, but x naught. Okay, we will fix it. We will fix it. Particle is localized x naught, and the particle size is so particle localized around some coordinate x naught, and the size of particle is double delta x. So the width of this wave packet. Let's assume we can show, and we will show that later, that this f of k, the amplitude of the of waves are localized in the same manner around some k naught. It's localized around some k naught. Here is plus delta k. Here is minus delta k. Obviously, it's k naught plus delta k, k naught. So width of this packet is 2 delta k. We can write down our integral in that way, where we know that this f of k is localized near the sum k naught. That's our plane waves. And then if we know that the amplitude is approximately 0, far from the center of the the wave packet, we can limit the integral by this small region around this around this around this wave packet. So we can integrate near the small region here. And if we work near the near this k value equal to k naught, we can decompose the dependence of the frequency, our dispersion law, or dependence of the frequency on the wave vector k in the Taylor series up to the first order. The zeroth order gives us some omega k naught, or we can name it omega 0. And that's just the first correction, first order of the Taylor series, first correction to the dispersion law. Now let's introduce the variable k naught, k minus k naught. So just shift the center of our coordinate system. Note that we're still working in the in the space of wave vectors. So k is a wave vector, not the coordinate space. And this integral can become. I can show it how. Let's show how we can go from equation 3.5 to 3.7. Can you say, do you need this precise explanation of the derivation of these equations or not? Can somebody answer? Okay, let's assume. Do you hear me? So can you say that, do we need to describe in detail the derivation of the equations, or we can I can just show the main equation? What is more convenient for you? Guys, please give me a feedback.
Okay, can you show the teacher?
Yeah, sorry, can you repeat it?
Can you show me the details of the equation?
Okay.
Show me more details.
Okay.
Okay, thank you.
Yeah. So we have this. We have this equation, and so what we do, okay. Do you see how? Oh, you should. Okay. Give me a second. I change. Yeah. You should see this window. Yeah. I think so. So we will substitute the omega by its decomposition in the Taylor series, and then we change our we make this change of the our variables. We know that dxi equal to dk. That means that we can rewrite this. Okay, let's do it that way. Yeah, we rewrite this integral. So k minus k naught can be substituted by psi. Here, k minus k minus k naught psi, and here is a k, and we can express k equals to psi plus k naught, so we can substitute it in that way. Okay, we see, and d psi equals to dk, so okay, right, d psi. So we see that we can decompose exponent in the following form. Sorry, let's do it in that way. We know that E times A plus B equals to E B A. So we can decompose this expression in that form. Then we see that this term do not depend on psi, and we can just move it before the integral. Here's it. Here it is. And here we can simplify this equation, just factorizing it. I can factorize here I, and psi. So yeah, that's it. Yeah, and we need to change our interval in that way. So that integral, we can see that integral is the same as that one. It's the same thing. So what we have done, we just substituted k by psi plus k and k minus k naught by psi, and just moved the factors that do not depend on psi from the integral before the integral. Let's look on this function. We can find the absolute value of this function. Absolute value, if you're familiar with complex numbers, absolute value of e times I phi, where phi is a real number, equals to 1. That is why if we try to find out the absolute value of this function, absolute value equals to 1 over squared absolute value 2 pi. The absolute value of e, this factor equals to 1, and that means that we stick to the absolute value of this integral f of psi times I psi x minus d omega dk times t, sorry for my writing, d psi. But if we look closer, we see that this integral, this integral, this function do not depend on x and t separately. it depends only on the combination x minus d omega dk times t. And if this value if we change x and t in the matter when this value do not change, the absolute value of psi will not change. That means that there's the point. Okay, let's draw equal to constant. Let's draw this function. Everybody knows this function. It's t. It's this our function. Some linear. That's the constant, and the tangent of this alpha is given by d omega by dk. Yeah, that's just a linear motion, and that means that if you move in time by some value delta t, and simultaneously move in space by some value of delta x equal to d omega dk times delta t, you would have the same you would have you will have the same shape of your wave packet. So you have this one here, this one here, this one. But if you move far in time or in space, the amplitude would be approximately 0. So that means that this bell-shaped wave packet moves in time, moves in space with the velocity that is given by this value. So that is the velocity of the movement of this wave packet, d omega, the derivative of the omega by k, that is taken at the center of the wave packet, and that velocity is called group velocity. Note that we have two velocities. First velocity is the velocity of the phase of the our wave, and another velocity is the velocity of the movement of the packet of this wave. That's the different velocities. Probably I'm sure that most of you knows about that because you're learning at the physics department, and you're learning about the transition of the information, and that information is transferred by this wave packets. But I want to show you this cute picture from the Wikipedia. I'm sorry, not that one. That demonstrates. Let's take this one. That demonstrates the difference between the phase speed and group speed. The red dot describes the phase speed of the phase of the wave packet, and the green dot is a group speed. You see that the node of the wave packet, or the peak of this wave packet, it propagates with the speed of this green dot, and the red dot propagates much faster than the green dot. And you probably know, but I have to repeat that the phase speed can be faster than the group speed, but the information that you but you can transfer information only with the speed of the group. You can transfer the information of the only by the with these packets, with the wave packets, but not phase cannot transfer the information. Only the group speed can transfer. Only the wave packet can transfer information, and that is the and that is why the group speed never can exceed the speed of the light, because you know from the special relativity theory that nothing can be faster than you cannot transfer the information faster than the speed of light. You can transfer information only with the speed of light or slower, but the phase velocity can be faster than the speed of light, but you cannot transfer any information with a phase, only with a group speed. So let's and that is mean that only a group velocity can describe the movement of the particle, which is the movement of particle is the movement of this wave packet, and that means that group speed, the velocity of the particle, is the d omega by dk. But from the classical physics, I'm sorry, can I have 5 minutes? Is it okay for you if I will be a bit late for 5 minutes?
Yes,
Yeah,
I
of
think
course.
that,
Yeah.
Okay. We'll continue in the next session, but last thing I want to say that in classical physics, you know that the velocity is a derivative of the energy by the momentum, dE by dP. For free moving particles, d by dP is for free moving particles, E equals 2 masses, and dE by dP equals to 2p divided to m equals pi m. So that is the velocity. That's the classical well-known equation. And comparing this equation and this equation, and we know that our assumption is E equals to omega h omega. Okay, let's move it here. We find that V equals to h d omega dp equals to d omega to d pi divided by h bar. So if we compare this equation, this one with this one, we see that k the k, which is the wave vector, equals to momentum divided by h bar, or vice versa, momentum equals to h bar multiplied by wave vector, or h divided by, if we know that k is 2 pi divided by lambda, with lambda wavelength. So the wavelength, so from this analysis wave packet, an assumption that energy equals to h omega, we found that the momentum of the wave packet can be described as the multiplication of the wave number k and the Planck constant. So the next lecture we will analyze the movement of the Gaussian shaped wave packet, and we will derive the equation of the evolution of the wave packet. And which we will show is the Schrödinger equation. So if it is no additional questions, I have to say goodbye, and we will see you tomorrow at the same time.